Hey everyone, this is Mr. Ting, and welcome to part 3 in my series on how to conduct an EEI. Now, do know that this is coming from a science high school teacher in Brisbane, Australia. But of course, the stuff that I'm talking about does apply to science investigations generally, so I'm sure there's something that you'll still get out of this if this is what you're interested in. If you haven't seen my first 2 videos yet, you might want to watch that. But if you've seen that, or if what you're after is figuring out how to process data from an experiment, you've come to the right place. So you've finished your experiment, you've got all these numbers. What do? Right? You've got this data. It's so exciting. Personally, it's the most exciting part of the entire investigation process. I mean, it's where you see whether your hypothesis was supported. It's like, did you actually find something, right? To me, it's one of the most exciting parts. Well, the problem is you don't actually have data. What you've got is raw data. This is stuff that's unprocessed, that's unrefined. It's just the numbers that you got straight from, your readings. Now, for some people, they might think this looks pretty impressive and they might actually stick this straight into their science report. But the problem with that is, well, this doesn't make sense. So this is data from the example that I gave in the previous video of the effect of high or low pitched music on plant growth. And if you showed this to someone, you're like, hey, what do you reckon? They'll go, what does this even mean? So did you find anything? Right? It doesn't make any sense. You need to do the hard work of converting raw data into results, into refined process results. So that needs to turn into this. And I mean, look at that. That makes so much more sense. Big no-no for this. So we're going to talk about how that actually happens. But I need to make this point very clear. You have to process data. Do not put your raw data in your final report. That can go in your journal, but it never makes it into your final report. Now, why do we process data? Well, firstly, the whole point is to see whether your hypothesis was supported or rejected. And processing data helps you do that. It also lets us look at the overall pattern because we're really not interested in the little details. I mean, you shouldn't be. And remember also that the whole reason why we did repetitions of tests was so that we could get an average. It's not so that we can display every single test. The purpose is to see the overall trend, the overall pattern, not the individual things. And finally, well, we process data because when we're writing the report, the whole purpose is to communicate it to people. It needs to make sense. It needs to be clear to the reader. Like you saw before, if it's just numbers and the reader looks at it and they're like, what is this? You have not accomplished your mission. So how can we present the data? Well, one really good way of doing it is as a table, of course. So you set your table out like this. Well, what goes where? There's a very simple rule of thumb, and it's this. The independent variable always goes on the left, and the dependent variable always goes on the right. Easy peasy. Next, creating a graph. Is there a rule for this too? Well, yes, there actually is. And of course, it's that the independent variable always goes on the X and the dependent variable always goes on the Y. This is a non-negotiable. This isn't like, maybe in most, it's like all the time, it's always like this. The rules that you might have heard about, like, time always goes in the X, or like, that's not true. Time is sometimes the dependent variable, and time might actually go up this way. So don't think about like, no. The rule is just IV goes here, DV goes there. Okay, so another way of saying it, independent variable goes on the horizontal, dependent goes on the vertical. Or sometimes I tell myself, well, Y depends on X. So whatever variables there are, Y is the one that's got to change as a result of X changing. Cool. Well, the next question is, all right, so that's what your graph looks like, but what type of graph do you actually use? Well, in science, the 2 main graphs that we use are bar graphs and line graphs, right? So bar graphs will look like that, and line graphs look like that. Hang on, we've got a bit of a problem here, which is that in science, we never ever join the dots. Like, this is something maybe that can work in some cases, but in science, no. We never ever connect the dots in science from an experimental investigation. And so really, your choices aren't between a bar and a line graph. It's really between a bar and a scatter plot. If you haven't heard that before, congratulations, you get to hear it now. A scatter plot looks something a lot more like this. It can be confused for a line graph because there's a line, but it's a little bit different. This time it's a line of best fit, and note that it's not going through the points, right? It's just showing where it's generally going. Anyway, which one do you use? Well, there is a very simple rule as well, and it's this: if your independent variable is discrete, use a bar graph. If your independent variable is continuous, use a scatter plot. What do those words mean? Discrete means that it's categorical. It's a different category. For example, Maybe like you're comparing stuff from Brisbane to Adelaide to Perth. Like those are just completely different categories. Or like, the effect of green or blue or red. They're like, they're actually different colors. Continuous would be something that's numerical or quantitative. So that's using numbers. Maybe instead of using colors, you decided to like compare wavelengths of light. So it's like, 300 nanometers versus 600 nanometers wavelength. That now is a continuous version of the independent variable, and therefore should be a scatter plot. Okay, that was a bit confusing. Let me give you some examples. Example number 1, yum in the sun. What type of graph would you use if you wanted to see the effect of temperature on ice cream sales? Well, the first question is, what's the IV and what's the DV? The independent variable, in this case, the one that you're testing, is temperature. You want to see the effect of temperature. What's depending on that is ice cream sales. So is temperature discrete? Is it categorical? Or is it continuous? And the answer is, well, it is continuous, right? It's just numbers that continue. Therefore, the data should be shown as a scatter plot. So here's an example of some fake data that I found. Temperature, of course, has to go on the X because that's independent, and sales, ice cream sales, has to go on the Y because it is the dependent variable. So I get my data and it looks like this. Beautiful. Now what? Is that good enough? Well, I mean, kind of. Well, okay, there are a few things I don't like about this table. For example, there is no title, and we really should have used the $ unit like as part of here, so like sales bracket dollars, kind of like how we put degrees Celsius here. But apart from that, I mean, that's kind of complete. Well, we could make it better. Like we could actually show a trend line. So that's like the line that kind of best shows where the data is going, or as I called it before, the line of best fit. And the line of best fit will look something like this. Now, some of you are going, oh yeah, that makes total sense. I can see that. And some of you are going, hang on, I thought the line of best fit, starts from here. I thought it needs to go through some like more of the points. And those are basically some of the most common errors that students make when they try and draw this line of best fit. They make it start from the origin. There is no rule that it needs to start from the origin, or they'll make it kind of pass through dots. It's just meant to show where the lines are generally going. Now, the best way really to do this is not to do it by hand. It's to use a program, of course, on the computer. If you do it in Excel, for example, or Google Sheets, there are options in there to add a trend line. If you don't know how to do it, just find it out. It's an easy Google search will show that to you. So there you go. Now, what do we do with the ones that kind of stand out? So like this guy over here, which we would call, I guess, an outlier, an anomalous result. Well, if this was probably because of a mistake, then you probably shouldn't have included it in the first place. Like if you have good reason to believe that it just shouldn't be there, don't include it. Otherwise, it's just going to affect your data. But if it's just something that simply stands out, you've got no reason to believe that there was any mistake, then you have to include it. Like you can't fake it and just remove it because it doesn't fit with your data. But there's no need to comment on it. And this is another thing that students do wrong. They kind of see this and they go like, oh, well, this. But there was actually one day where the temperature was, this, and ice cream sales wasn't as much, which is a bit strange. No. Who cares about the individual points? We only analyze overall patterns. The point of all those dots was so that you can make that line. And all you now talk about is that line, not the dots anymore. Yeah? That's really, really important for me to stress. So when you're describing the relationship, we would call this a positive relationship, or a positive correlation. That's another word for it. When you've got data that's like this, there's obviously a relationship here. As X is going up, Y is going up as well. This is what we will call a negative correlation. When X is going up, Y is going down. And this one, what would your line of best fit look like? Would it look like this? Or this, or well, there's no line of best fit you can draw, and so this would be an example of no correlation. The conclusion from this is that there is no relationship. Now, there is a better way of mathematically analyzing this, and this is in a separate video which I've made on statistical tests for high school students, which I will include as a link on the screen now. So watch that in your own time. It's a much more complex video, but it is worth watching if you want to find out some more robust mathematical ways of analyzing your data. Okay, example number 2, musical plants. So this is from the previous video. What type of graph would you use if you wanted to see the effect of high-pitched music on plant growth? Same question as before. What is the IV? What is the DV? Well, in this case, the independent variable is the pitch of music, and the dependent variable is the plant height. Is the IV discrete, or is it continuous? Oh, tricky question. I mean, the pitch of music, you can actually describe that in numbers, but in the last video, I decided to just use high pitch, low pitch, and no pitch. I mean, no music, right? So in that case, it's just like either yes or no. So this is the numbers that I'm talking about. These are just words. So it's discrete, they're categorical. Therefore, the data should be shown in a bar graph. Now, if I do this right, hang on. Yeah, magic. Ta-da! So here's the bar graph. Oops, not bar graph. Here's the raw data that needs to be converted into a bar graph. How do you turn into a bar graph? Well, believe it or not, some students will do this. They'll select everything, insert, and then the bar graph, and that. And I am like, I wish that that this was false and that I was lying, but people will literally submit this in their report, right? Like this is what they will show. Maybe they might get rid of this. It's like, when you put legend at the side, and they're like, here you go. This is my data. What does this even mean? I mean, like, is it possible to analyze the data and compare it? Well, I mean, kind of. I guess I could look at no, I can't. Like, this actually does not make sense. Do not do this. If you create the graph and you look at it and you're like, oh, I don't know what that means, but oh well. You haven't done it right. One rule of thumb I actually use for my students is that after they finish their final graph, they should be able to show it to anyone, like, I don't know, a parent or something who can, read basic graphs. And that parent should be able to understand it within 10 seconds. Like, really quickly look at it and go, oh yeah, I see what your experiment was all about. And you cannot say this for this graph. It just doesn't make sense. In other words, this actually needs to be turned, into like another table. It needs to be processed before it can be converted into a graph. So let's turn it into a much more proper table. What does the table look like? Like I said before, the IV goes on the left, DV goes on the right. What's the independent variable? In this case, it's I guess the type of music played, but one also had no music. So I'm just going to say growth condition. And what were my growth conditions? Well, I had high-pitched music, I had low-pitched music, and I had my control, which was no music. And what's my dependent variable? Well, my dependent variable in this case was plant height, right? So plant height. But then, hang on, I've got two plant heights because I measured the height at the start and at the end. Is there any way I can combine this into one number? Well, yes, I can. Because, I mean, since I was looking at growth, why don't I just look at the difference? In other words, what I'm actually calculating is height increase over the 3 weeks that I conducted this experiment. But I've got so many numbers, right? Because I did each one 10 times. So this should be average height increase in centimeters, because that was my units in the first place. And that's so much better now. Now I'm going to spare you all the mathematical calculations that I had to do. I used Excel really just to do all the calculations. But the averages are this. 11.2 centimeter increase for high-pitched music, 8.7 for low-pitched, and 8.5. Awesome. And this is my table. Getting rid of this. This is all I need to show as my table of results in the report. Yes, it is that easy. And then what does my graph look like? Well, select this, and then let's make that graph. It's going to be a bar graph, not a scatter plot. Bar graph. And that's it. Well, okay, not completely. Let's fix up a few things first. Let's fix the title. Let's go effect of music pitch on plant growth. We probably should also add the axes title so that we're accurate there too. So this is going to be average height increase in centimeters, and this is going to be growth condition. But otherwise, that's it. This is what I put in my report. But hang on. I mean, this looks so much more complex and impressive than this. This looks so boring. This looks like nothing. It looks so simple. But it wasn't simple, was it? I mean, you actually had to put a lot of work to convert all those numbers into this and then into this. So behind the scenes, there was a lot of work, right? It's an incredible stage production, but you don't see what goes on backstage. The point is that this final graph needs to just be simple, clear, make sense to the reader. If you look at this right now and I said, hey, my experiment was about seeing what music did, you'd be able to go, oh yeah, I can see high-pitched music made the height increase by much more than low pitch and control, right? Within 5 seconds, you're already telling me the conclusion. This is brilliant. A+ right here. That's everything that you need for the graph. So don't be fooled by its simplicity. Don't think, oh, I'm not going to get an A+ because it's just no. That's actually what it's meant to look like. So that is perfect. I do want to add one extra thing, which is the fact that I'm just putting numbers so you can see it. Some people actually say, well, 8.7, 8.5. So it looks like low pitched music actually did better than the control. Well, not really. I mean, 8.7 is hardly a difference from 8.5. But how do you know it wasn't a difference? Well, it's pretty hard to know how big the difference needs to be before it's really significant. And once again, that's that other video that I was talking about before where I look at statistical tests. I actually look at ways so you can compare groups and come up with a number that mathematically actually shows whether the difference is significant or not. So again, have a look at that video if you get the chance. It will just make your results and your analysis of your results much more robust. How good is that word, robust? It's just such a robust word. So in summary, raw data must be processed. Do not dare put raw data into your report. It should only show the final tables and graphs. In a table, IV goes on the left, DV goes on the right. In a graph, IV goes on the X, DV goes on the Y. If the IV is discrete, it's a bar graph. If the IV is continuous, it's a scatter plot. Always discuss the overall pattern, never the individual points. If possible, use further statistical analysis. So that's that other video that I'm now talking about for the third time. Hint, hint, wink, wink, nudge, nudge. And finally, your graph should be easily understood. If you've done that, 2 thumbs up to you. You have processed your data. And that brings us to the end of this one. In the next video, we're going to have a look at writing the report, specifically the first part of the report. I will see you there.